Well, thank you, everyone. Welcome. So I brought some hardware, or rather I didn't. Actually, James brought some hardware up from the lab. I'm going to tell you about Liger, which is a next generation adaptive optics instrument for Keck Observatory. Um, I get to be here presenting on behalf of a wonderful team of scientists, engineers, technicians. Um, so I'll just start with a little bit of that. Many of these people are here, students who have worked on Liger or are working on Liger, highlighted in blue. Students who have graduated with their PhDs largely based on Liger are in green there. There's some photos of them. Some of these people are here in this room. And some of what they've worked on and built is right here on this cart. So as you can see, this is metals being cut. We have some prototypes. We have some real pieces there. Very exciting. So I'm going to tell you more about Liger, what all these wonderful folks have been doing, what it will do for your science, and where we're at with the project. All right, starting off, I want to give you an overview. So like I said, it's a near-infrared adaptive optics instrument for Keck. It's an imager. So here's the overall field. You have an imager and then selectable modes for spectroscopy. Now, this is integral field spectroscopy, hyperspectral imaging. I'm showing here an example of one of them. So this is one of the lenslet fields. And the idea is if you select that broader orange one, you target a field of view, and this is simulated data. So note, we're able to end-to-end simulate what this instrument will deliver. This is looking at a lensed quasar system. So A, B, C, D are all multiple images of a background quasar gravitationally lensed by this galaxy in the center here. If you want to hear more about why that's so exciting and all the great science you can do with these systems, in particular for cosmology, you should show up tomorrow for Tommaso Treo's plenary talk. I'm not going to get into it here, but this is a key science case for Liger. Okay, so this is not just an image. This is an integral field unit. Oh, yeah. Ah, thank you. I talk loudly. Okay, so that means every pixel here, it has a spectrum. They're spaxels. So the lensed image D of the quasar comes out here, and you have, you can see from the quasar this lovely broad H alpha emission, as well as metal lines from the narrow line region, which are very powerful for cosmology. They're just showing their comparison. The green is the Liger simulated spectrum relative to blue. That's the throughput that we currently get on Keck with OSIRIS. So you can tell there's a bit of an advantage there. That's just one of many. Drilling down a little more. So that's a sense of what this instrument does, right? Plus an imager along the side of there. So next generation AO science. Liger is designed to supersede OSIRIS. It will retire the current OSIRIS instrument and will do a lot of new things that Keck currently is not capable of. That drives a lot of exciting cutting edge science that we'd like to do over the next 2 to 3 decades. So the main advantages, some of the key ones: improved spectral resolution, okay, with selectable modes. So our 4,000 to 10,000, higher sensitivity, higher and selectable fields of view, expanded wavelength coverage, and a few other things. And one thing to emphasize is Keck Adaptive Optics has gotten a lot better. It is continuing to get better. Liger is built to take full advantage of the COPPA system, which is coming online very soon, and to take advantage of future improvements that we envision, again, over the next many years. Right now, it's in the fabrication phase. As you can see, it's being built. Various components are being tested, machine fabricated. And it's on track. Our aim is for delivery, if all goes very well, late 2028, commissioning, or early 2029. So imagine in a few years you can do your science with Liger. One quick thing now on the name. So Liger, it's not an acronym. It's a big hyperspectral cat. I mean, instrument. So the Liger is an animal, okay? It's a real animal. It's a hybrid between a lion and a tigress. It's the biggest cat in the world. This is my excuse to show a super cute baby animal picture here. The Liger instrument is a hybrid design between the IRIS spectrograph for the 30-meter telescope and Keck Adaptive Optics imager design. So that's the name. Again, not an acronym. It's a name. It's named after the big hybrid animal. Here's our rendering, our mock-up of the full instrument. So very advanced. We finished the final design a couple years ago, and it's cruising along. Okay, so this is the Keck Science meeting. I'd like to tell you about some of the science. I'm not going to tell you about anywhere near all the science because it's broad, and that's part of the point. There's a broad set of new capabilities that I mentioned earlier. This flows to from five key science drivers, which span a large range of astrophysics. So from the galactic center, black holes, galaxies, extrasolar planets, and that's just part of it. And we have a lot of other science use case examples that our science team has developed over the years. Again, this is very much a partial list. And what's most exciting to me is, well, we don't know yet what we don't know. So LIGO is built for a workhorse instrument to deliver future science with new discoveries that we're not imagining quite yet. Again, for many years to come. So with that said, I'll show you some of the science we do envision. Start off with some of the most exciting Keck AO science, one example of many. But if you ask the Nobel Prize Committee, I think they might point you towards this one. So the galactic center, where there are a lot of stars orbiting the supermassive black hole, and you can track the motions, the orbits of those stars. And spectroscopic radial velocity monitoring gives you a lot of information. And with LIGO, you could do some next generation tests of general relativity and other fundamental physics. So shown here, you've got the galactic center with a few different instruments. This is, again, the simulation, what LIGO will see. This is Tuan Do's work with Andrea Ghez and others here at UCLA, tracking the orbits of the stars, okay? And fitting them with a general relativistic model. So with LIGO, you can take this to the next level. You can reach down to shorter period stars, right? Because you have to watch these things as they orbit. You can measure the orbital precession. It's a key test of general relativity. That's a difficult measurement. It requires a very stable instrument. LIGO delivers that. We're spec'd out to do that. You could do a lot of exciting things. Is there an extended mass profile, a Bacall cusp of stellar remnants? That's a very interesting, theoretically predicted, result that's not established yet. So, and there's more that I won't get into. You can ask Andrea or others here. Another key thing is the field of view. You can cover this all of these nearby stars or these galactic center stars, the S stars, simultaneously. So you notice a couple of different images up there. Okay, again, these are data cubes. I want to drill down on that a little bit. You might wonder, okay, LIGO, near-infrared spectroscopy. I've heard about this thing called the James Webb Space Telescope, right? It's very powerful. It's amazing. There it is, looking at the galactic center. It's amazing. It really, really is, okay? That's what Keck can do now with OSIRIS. This is what LIGO will be doing, okay? And you can see a bit of a difference, right? Okay. And you might wonder, wow, really? And the answer is yes, really, okay? So LIGO delivers this because Keck's bigger, you have a better diffraction limit and much finer sampling, okay? So you can see that advantage there. Something that's, less obvious from the images is we also have 3 times the spectral resolution, okay? So this is comparing current Keck OSIRIS with LIGO with a higher spectral resolution mode. You can resolve a lot of these lines. That's very important for some of this test, as well as other fundamental physics. That's a big part of the science case. Okay. I'm going to blitz through a bit of the rest. Another very exciting topic is black holes across all mass ranges. On the upper mass end, okay, so I'm showing black hole mass. This is many decades of mass and their number density, okay? Supermassive black holes up here, they're found in the centers of galaxies, but where do they come from? How did they get there? Okay, down in this range, the upper end of what we call stellar mass black holes that we're seeing with gravitational waves, how did they get there? How come they're so big? Okay, in the middle range, do black holes even exist in this space? Are there intermediate mass black holes? So LIGO, with multiple techniques, will be able to search for, characterize, measure the masses of black holes in these ranges. That's very exciting. One more quick one, near and dear to me, is the growth of galaxies over cosmic time. They start out small and clumpy and irregular, and they get much bigger, and they develop spiral structures. So when and how did that happen? And this is a key area where LIGO, with its sensitivity, spectral resolution, field of view, and other advances, will be able to really address these questions of how do galaxies grow and evolve and form their structures over time. Okay, I'm going to stop talking about the science there, but trust me, there's a lot more. A little bit now just on the activities and timeline. Team's been busy. Technical team has been quite busy doing great work. You can see some of the fruits here. The fabrication phase is underway. We'd like to very much thank the Moore Foundation, Heising-Simons Foundation, National Science Foundation for their support. Again, if all goes well, if it keeps going well, we're aiming for commissioning in early 2029. Meanwhile, science team has set top level requirements from the instrument. We're good there. In the hopefully near future, we'll be reviewing and participating in the science verification, making sure it delivers what we need to do our science, to do your science. That said, you've seen some examples of simulated data. I just want to emphasize, we have full end-to-end simulations. If you're wondering, can I do this crazy idea with LIGO? Get in touch. We can try it with the simulator. We can give you an answer to that. So please do feel free to get in touch. There's my email. You can find me. And we'd be happy to have you contribute on the science team as well. With that, just a little bit more on the fabrication progress. Some great images. There's a detector coming in. There's a really big cryostat, actually two really big cryostats. One of them is down here in the basement. Great stuff. And I'll leave you there with the summary. So this is a powerful, capable, workhorse adaptive optics instrument for your science, our science, for decades to come at Keck. Thank you.